All right, so no more questions? We good? We're moving on. Chapter 1, sand and water. Sand can be annoying because it's so small that it sticks to everything. And sand, like all ordinary matter, is composed of tiny particles called atoms, which are unimaginably small. But a single grain of sand contains more atoms than there are grains of sand on the largest beach. I was trying to think about, I can't remember if it was like Plato who first came up with this idea, but I just imagined him being like, all right, so what if I ripped that thing in half? Like if you took a piece of paper and ripped it in half, and then ripped it in half, and kept doing that forever, would you finally get to a piece of matter that you could no longer rip in half? And that is this theory. That's atomic theory, is that the atom is the smallest indestructible particle, well, was the smallest indestructible, and then we built the Large Hadron Collider and smashed them together and found out there's even smaller pieces. But the idea that matter is composed of tiny particles is among the greatest discoveries of humankind. And you'll see why. Because to understand how matter behaves, we have to understand how the particles that compose matter behave. So for something like a water molecule, it's not just the fact that it's two hydrogen atoms, right? So we got two hydrogen atoms and then a single oxygen atom. It's not just that. It's the fact that it's in this particular bent shape. That bent shape is what gives water its properties. Because you can have other molecules that are just, three atoms stuck together. But we'll get there. Building blocks. So there's a direct connection between the world of atoms and molecules and the way we experience things every day. As chemists, we will explore this connection. Chemistry is the science that tries to understand how matter behaves by studying how the atoms and molecules behave, right? So if we can understand the smallest piece, then we can determine something about the whole. Sociology is kind of like this, right? We try to understand people to determine how they'll behave as a group. Chemicals compose everything. A lot of the, I'll just go ahead and say media, news outlets, they love to portray chemicals as these bad things, but literally everything is a chemical. So if you ever see chemical-free sunscreen, it can't even be air, it has to be a vacuum, because air is a chemical as well. But they make up everything. And so the popular conceptions of chemicals limit them to these dangerous poisons or pollutants. But really, it's the dose that makes the poison, right? You can drink so much water that you die. So in that way, water could even be a poison. You've probably, or you might have heard of dihydrogen monoxide, scientific name for water. But people have written some pretty funny ad campaigns about how bad dihydrogen monoxide is and how it needs to be banned. Right? So ordinary things are chemicals too. The water we drink, air we breathe, the food we eat, medicines, our bodies. All of these things are chemicals. And again, if we can understand how they work at the smallest level, we can exploit that, really. That's how we have electricity, is by exploiting the way water works. Almost all electricity is made by turning water into steam. Almost all of it. The exceptions would be wind turbines, which you could arguably say there's water in the air, so that's steam, and solar panels. So the scientific method, though, is the sort of thought process that we use to figure out things about chemicals. It's not a rigid procedure that automatically leads to a definitive answer. This isn't World of Warcraft. You can't go and do a set of tasks and get the magic sword. It's very, very nebulous. As somebody who's just finishing their PhD, it's very, very nebulous. And this differs from ancient Greek philosophies. This was a crazy one that I didn't know before. Greek philosophers used to think that onions and garlic would make magnets not attractive. And until surprisingly recently, it was like 1680 something or so, and somebody was like, hey, I tested this and it doesn't work. But for the longest time, they were like, oh yeah, somebody else said it, so it must be true. So for the scientific method, right, nobody had tested it before. But now, we have this scientific method to sort of guide the way we think about things. And there are 4 key characteristics. We make an observation, right? So we could say, oh, magnets stick to each other, at least in certain ways. And then we can formulate a hypothesis. Garlics will break those magnets. And then you can test that hypothesis. And apparently nobody had done that for hundreds and hundreds of years. But we could go now and buy a magnet, and you could buy garlic, and you could stick them together and see that the magnet still works. But sometimes, actually, I won't just say sometimes, every time, it's not quite as simple as that. So by testing these hypotheses, we can formulate laws and theories. Am I going too fast? Good? All right. This is pretty simple stuff. So our starting point then are these observations, right? We talked about onions and magnets, garlic and magnets. But another one might be is like, I talk too fast when I have too much caffeine. So we might test a hypothesis. We say, okay, yeah, I'm talking too fast when I have caffeine. My hypothesis is I'll talk slower if I don't drink caffeine. So then we would go and we would test our hypothesis. From there, we would either confirm or revise that hypothesis. Maybe I just talk really fast. Maybe it is the caffeine. But let's say it's not the caffeine, there's just something wrong with me. So you have to come back and do a hypothesis, and then maybe you go see a psychologist and talk to them about your mom and your dad and other things and find out that's why you talk really fast. Sorry, that was a terrible example. But the idea is that we test recursively. So that means that we give a hypothesis and we test it. Give a hypothesis, revise it, maybe we throw it out altogether. You might say, a better example would be like fuel efficiency in your car. Most of the time now, you get like, right, or at least the newer cars, they'll give you your miles per gallon. And so your hypothesis might be when I drive uphill, then I get worse gas mileage, right? Lower miles per gallon. Pretty easy to test, except you have to think about a lot of different things. How steep is the hill? Do you have a tailwind or a headwind? How many people are in your car? How much stuff are you towing with your car? So there's a lot of factors. Are you driving with the windows down? There's a lot of different factors that you have to consider when putting together these experiments. So, right, our first step is to make an observation. Let's say gas mileage is bad going uphill. That would be one that we could maybe make with the naked eye, right? If you keep track of your odometer and the amount of gas that you burned, and then the next time you fill up, you do the math. Or you could rely on a sensitive instrument, like your car's internal computer that's calculating your miles per gallon. But these usually rely on making measurements, maybe I should underline this, measurements or descriptions of some aspect of the physical world. So as an example of this, a more scientific example, Antoine Lavoisier and his wife, Marianne Lavoisier, studied combustion by burning substances in closed containers. I don't recommend this. Don't try this at home. Things explode that way. But they observed that the mass in these containers where they were burning things didn't change during that combustion. So at that point, they had an observation. So they said that, our hypothesis here. Hypothesized that combustion of air involved a combination of a substance with a component of air. So there's something in there happening, but only with stuff in that container. And this is very important. A good hypothesis is falsifiable. It could be proven wrong, like the Earth is flat. A non-falsifiable hypothesis would be trying to prove a negative, right? Trying to prove that nobody is 10 feet tall. You couldn't do it because you'd have to gather every single human on Earth and measure them all and say, oh, none of them are 10 feet tall. Or to say that every grain of sand, or there's no grain of sand out there that has a tiny little smiley face on it. You can't prove that one wrong. So that's a bad hypothesis. And again, we test these hypotheses by our experiments, and they have to be highly controlled. Like in the example I was talking about, your gas mileage. If you think you're driving on a flat road, it might have a slight gradient. So you have to do your test on that same stretch of road every time. You have to think about the amount of gas in your tank because it's changing the weight of your car, which changes how much gas you need to drive the car at a certain speed. Speed also matters. So you have to do these in highly controlled ways. and they're designed to validate or invalidate hypotheses. If the experiment shows the hypothesis to be incorrect, it may be modified or discarded entirely. If revised, then you test the hypothesis again. So the goal of these hypotheses in science is to come up with either scientific laws or scientific theories. A scientific law, this one's important, is a brief statement that summarizes what happens and predict future observations. So the law of gravity. Right? If I take my keys and I let go of them, they fall to the ground. Based on the law of gravity, we could say that every time I do that, my keys are going to fall and hit the ground, which is different than a theory. Or, using the Lavoisier example again, he developed the law of conservation of mass. So in a chemical reaction, matter is neither created nor destroyed. Now, on the other hand, we also have theories. Theories are models that provides an explanation for observations and laws. A model, and generally models of the way nature is. So we want to use models to predict behavior well beyond the observations on which they were founded. And the key here would be they provide an explanation. So this is the why of the law. Lavoisier's law eventually led to John Dalton's atomic theory. Not the first to use the idea of the atom, but the first one to really put it into press, I suppose. So Dalton proposed that all matter was composed of these small, indestructible particles called atoms. So matter can't be created nor destroyed. Maybe it's made up of tiny, indestructible particles. I already have some highlights on here. So a law, I'm going to erase this and rewrite it because it's that important. A law states what happens, and it arises from observations, may be proven false, but a theory tries to explain why things happen. Again, though, it arises from hypotheses, may be proven to be false, and it's as close to truth as science can get. So when we're developing theories, it's to try and understand the underpinnings of why things are the way they are. So I state this again because it's important. A law states what happens, a theory tries to explain why things happen. All right, so conceptual checkpoint. Which of these statements most resembles a scientific theory? So which statement resembles a scientific theory? When pressure on a sample of oxygen gas is increased 10%, the volume decreases by 10%. The volume of a gas is inversely proportional to its pressure. A gas is composed of small particles in constant motion, or a gas sample has a mass of 15.8 grams and a volume of 10.5 liters. Does anybody want to take a stab? Any brave soul? C? Hear a couple C's. Does anybody want to disagree? Any naysayers? Any challengers? No? So law states what happens, and a theory tries to explain why things happen. So yeah, we're looking for a scientific theory here. And so this first one is saying what's going to happen, right? If we increase by 10%, we'll decrease by 10%. Volume of gas is inversely proportional. That's basically what this one's saying. And then a gas is composed of small particles in constant motion. So yeah, that's our best, that is the scientific theory in this case, right? So again, remember that. It's why things happen. Yeah, it is true all the time that gases are composed of small particles in constant motion, but it's not explaining what happens. So it's telling you that they're in constant motion, and you could derive from that the idea of pressure, or you could derive other laws from that. Yeah. Yeah, it's a statement of why things happen. So like, you could say if you run out of gas, your car stops. But then the theory behind that would be a car engine needs gasoline to run. Yeah. Are atoms real? I sure hope so. Like entire life is like dependent on that fact. This image shows the kanji, the Japanese characters for atom, written with individual iron atoms on top of a copper surface. And really, in this case, we're kind of just seeing the shadows of those atoms. Because if you were to actually look at an atom, you'd need to bounce light off of it. But if you bounce light off of it, it'll move. So we've never actually observed a single atom, but we can see their outlines based on the way electrons deflect around them. So changing gears here a little bit, we'll talk now about analyzing and interpreting data. So let's say you've made a hypothesis, you've gone out and you've done a test, and you've collected a bunch of data, but what do you do with that data? So scientists like Lavoisier and Dalton saw patterns in a series of related measurements. So if you do an experiment, change a couple things, like I was talking about with your car. If you're driving your car, and let's say you drive it uphill, you drive it downhill. Let's say you try even driving downhill at different gradients. The steeper the hill, you might find the better your gas mileage is. And so it's learning to analyze and interpret data is one of the most important scientific skills. Because you can go out and collect data, but if you don't understand what any of the data means, what's the point? So pretend that you're an early scientist trying to understand the composition of water. So you take it, you put it in this experiment. You know it contains the elements hydrogen and oxygen. And you do some experiments in which you decompose different samples. So decompose meaning you're splitting it apart, separating the hydrogens from the oxygen. And you get the results shown in this table. Do you notice any pattern in your data? Anybody want to take a stab? So you got sample A, where you had 20 grams of water, 50 grams of water, and then 100 grams of water. Pattern I would pick out here is we're increasing the amount of water every time, or increasing the amount of water. And then as we increase that amount of water, what did I do? The mass of oxygen actually increases. What are you doing, iPad? Okay, right, so we get more oxygen every time. So we've gone from our 20-gram sample of water, we get 17. Then in our 50-gram sample, we're getting 44 grams of water. And then in 100 grams, we get 88.9 grams. So there's some relationship then between the mass of water and the mass of hydrogen and the mass of oxygen. But the other pattern that's a little less obvious here is that the ratio of the masses of oxygen and hydrogen is the same for each sample. And this may be something that's like, well, no duh, water is made up of a single oxygen and two hydrogens. But at some point, people didn't know that. So when we decompose these samples and we take the mass of oxygen, we divide it by the mass of hydrogen, which is really just done because then you get a whole number, and those are just kind of easier to look at. Every single time, it's about 8. And this variation between these samples is just experimental variation. You might not have had exactly 2.2 grams, because it's 2.2, and then however many decimal places after that, and that's going to change that ratio just a little bit. And this is another scientific skill, is recognizing when you're within the limits of experimental error. You're close enough to the answer every time. And this is actually really a good tip for, in general, if you're trying to find patterns, start dividing things. And if you start getting similar ratios every time, then you know you've kind of hit on something. Plotting things is another great way to do it. Speaking of plots, graphs are also super important in science. So data is often visualized using graphs or images like this one. Here we have the carbon dioxide concentration in parts per million plotted against the year. So we look at these x and y axes and note that this doesn't start at 0, but starts at 1860. And then our y-axis also starts at 300, doesn't start at 0. Or I guess it starts somewhere just below that, 250. But we can derive information from this graph. So we could say, okay, in the year 1940, what was the atmospheric carbon dioxide level? With the magic of technology, we can zoom. And we can see that this is 300. This is about, not 350, excuse me. Right, so this is 310. We're just over 310 right here. So we might call that 311. That'll get into, we'll talk about estimating the number of figures. Anyways, so then you could take the slope of this too, and right, you could do things like pick 2 points on the graph and say, what is the average rate over this time? How much is it increasing by? So how do you succeed in chemistry? First is to be curious and imaginative. So like, try and get into these experiments, right? I mean, they're Chem 20 experiments. They've been done probably 1 million times at this point. Somebody out there already knows what the answer is, but you don't know what the answer is. And so try to get invested in wanting to know it for yourself and wanting to see the results for yourself. Be willing to do the math. Be willing to take some time to do the math. It's really easy to skip steps like writing units down or to just do it in your head. But when you do that and then you try to come back to it later, you either A, just absolutely don't know what you did, or B, you think that you did it right, but you did it wrong and you can't tell what you did wrong. So always write down your units and always write out the math, especially on the homeworks, because that's where you're getting the points from. And be committed to learning the material. Even if you're not wanting to do nursing or chem or biology or some other math-related field and you're just taking this to fulfill a credit, you're going to do better if you commit to learning the material. And commit to putting in a little bit of extra effort outside of class to, like I said, go through the definitions, right? I think there's a whole section at the back that's like, these are the new words that you probably don't know from this chapter. Go through those and do the homework. And don't rely on Google too much. Especially when we do unit analysis stuff, it's so easy to say, even Siri, you'd be like, hey Siri. Oh, I thought I was going to pick it up. You say, hey Siri, what is 100 kilometers in miles? And Siri will tell you the answer. But don't rely on that because you're not learning anything when you do that. This is a really, really good quote. I like the idea that human beings can do anything the way they want, or anything they want to. They need to be trained sometimes. They need a teacher to awaken the intelligence within them. I'm not going to say I'm going to awaken intelligence in you, but to be a chemist requires no special talent, I'm glad to say. And anyone can do it with hard work. And I do want to add to this, I just finished this book called The End of Average, which basically says treat people like individuals, which is no duh. But remember that the class is going to move at a certain pace, and if you struggle with one topic, there's also somebody else probably struggling with that, but then you're also probably going to have another topic that really clicks with you, and somebody else is going to struggle with that. And so that's where I want Discord to be this place where if you're doing well in one topic, somebody else is struggling with it, post those questions on Discord, and somebody else can help you out. Because I really think teaching is the best way to learn something or to make sure that you have learned it correctly. So. Yeah. Yep. Yeah, exactly. So keep that mentality in mind. You have to be able to, if you can explain it to your grandmother, unless your grandmother's already like a PhD chemist, maybe. That's easy. That's too easy. You got to pick another grandmother. Notes about the text. The answers to all the questions numbered in blue appear in the answer section at the back of the book. So all the homeworks actually are those blue questions. They're all the odd numbers. So you can just go look at the answers. Try the question first, obviously, and then you look at the answer, and then maybe try to reverse engineer it. That's learning too. The exercises problems, they're paired. So if you have those blue questions, then the black question next to it is going to be related. And there's often actually more than just paired. There's like a chunk of questions that'll be the same sort of material. So you can go through those ones too, or if there's a blue one that's not assigned, right? Extra practice to make sure you really know it. It would feel really bad to be these guys. There was a rocket launched back December 11th, 1998, called the Mars Climate Orbiter, and it was the first weather satellite for a planet other than Earth. It came too close to Mars, and trajectory corrections were needed. However, the onboard computers were programmed in metric units, Newton seconds, but the ground engineers entered the values in English units, pound seconds. And because of that, I can't remember if the correction they made was either way too big or way too small, and the orbiter ended up crashing. It was a $125 million error, just because the units were wrong. You hate to see it. So, if you get your units wrong in this class, like, you're going to miss a couple points. It's not going to be $125 million error. But those good practices start somewhere, and they could start here. This could be it. You might look back on this years from now and say, man, I made a $125 million error. Chem 20 could have been the place that changed it all. And then you'll invent time travel and come back, and then you'll have a paradox, and it'll be a whole bunch of fun. I'm not selling learning units very well. So we jump straight from that into scientific notation. So science pushes the boundaries of the very large and the very small, right? So like a single, or 18 grams of water is 1 times 2 to the, or 6.022 times 10 to the 23 water molecules, which is just like a stupid, stupid, stupid number. And those numbers are really hard to deal with when they get that big, or if they get that small, right? Because if you think of a single atom, how much does a single atom weigh? It's a really small number. So instead of dealing with these really big, stupid numbers, we use things like scientific notation, right? So like, this is too long, but if you were to write this in scientific notation, it would be 6.9, 1.4 times 10 to the 10 light years. That's a lot easier to deal with. It's also a lot easier to write out. So a written number in scientific notation has two parts. There's the decimal part, right? That's our here 1.4, or here our 1.2. And it has an exponential part, where we raise 10 to some exponent. And you can take this, right, put it in your calculator, or this one, maybe it's a little easier because we have it written out already, and it should spit out this number. So really, this is a shortcut. It's shorthand for us when we're writing, and it helps you maintain your number of significant figures. But we'll get there. Right, so if we have, again, looking at our scientific notation, 10 raised to the 0 is 1. Anything raised to the 0 is 1. I think I saw a TikTok about 0 raised to the 0 is still 1. But 10 to the 1, right, that's 1 times 10. Really what we're doing here, right, is we're taking 10, and to the second, it means it's 10 times 10. 10 to the third is 10 times 10 times 10, so on and so forth. That's the number of 10s that you're multiplying together. That's what exponents are. But if we have a negative exponent, what you're doing is you're doing all of that, but 1 over the number of 10s that you're multiplying together. So we get really small numbers, right? Because if you divide by 10, that's small. If you divide by 1,000, that's even smaller. So there's shortcuts, right? You don't need a calculator to do this scientific notation. So you just move the decimal point to obtain a number between 1 and 10. And then you write the result multiplied by 10 raised to the number of places that you moved that decimal point over. So here, right, we move from here. You can say here, but if I'm not writing anything, you're not going to see anything. And we move it over 1, 2, 3 places. So then we do, since this is where we moved it to, we have 5.983, and then times 10 raised to the third. And then if we're moving it for decimal numbers, we move it to the right. Then we're going to do 10 to the negative. So we have decimal here, but we're going backwards. So 1, 2, 3, 4. That's why you get 3.4, because we move the decimal place to here, times 10 to the negative 4. Oh, man. It's fun to look at the national debt. Back in 2016, it was this $18,416 billion, which is a lot of money. I don't know if you knew that. So 18 trillion, if we convert this over to scientific notation, I'm actually going to rewrite it here. I've had people before in my classes tell me they hate the way I write 8s. So, right, you don't want to write that out. But we want to convert this to scientific notation. We want to make it smaller, so we've got our decimal place here, and we're going to move it to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 times. And we'll get 1.8416 times 10 to the 13. And of course, if you have commas in there already, you could just say 3. Wow, come on, iPad. 3, 6, 9, 12, and then move one more over, and that's 13. So that's your scientific notation. And again, if we wanted to go the other way, we can take our small numbers, make them a little easier to work with. Let's go 1, 2, 3, 4, 5. I wish there was something like commas for decimal numbers, because then you could do the same thing and just be like 3, 6, 9, easy. But there's not, and now I forgot how many of these there were. 5, right? So we got 3.8 times 10 to the negative 5. Any questions about scientific notation? Cool. You're going to be doing a lot of it. Significant figures are the way that we represent precision. A good example of this would be if you step on a bathroom scale. Right? I step on the bathroom scale, and it reads 242 pounds. I think to myself, I need to lose some weight. Then I step off, and I eat a cheeseburger. But sometimes we don't have decimal places like that. So you can step on a scale, and it might say 242, but if you've got a nicer scale, it'll say 242.5. And that's the level of precision, because there are even numbers after that that represent your true weight, but they go on to infinity. On the contrary, we have things that we call precise numbers. Wow. Exact numbers. So like counting pennies, they're exact numbers. If you have 7 pennies, you have 7 pennies. There's no question as to whether or not you have like a tenth of a penny there. You would see a tenth of a penny. You think, how'd somebody get a tenth of a penny? But if you have 7 pennies, that's 7 whole pennies. On the other hand, like this gold bar, if you put a gold bar on a scale, it'll read out 10.0. But if you get a nicer scale, it might read 9.999. I think I added too many nines there. But point being, it might be actually less than 10 grams, or it might be a little bit more than 10 grams. And so when we do science, when you do the science, you need to keep track of how precise you were, because your numbers will change. Your results will change depending on that precision. For example, scientists have concluded that the average global temperature has risen by 0.7 degrees C since 1880. I think that's outdated now. But this is based on the analysis of records from thousands of temperature measuring stations around the world. So reporting the results differently does not convey the same information. If we add zeros, 0.70 is, in terms of measuring the temperature around the entire world, a lot more accurate. And adding 2 zeros is even crazier. If you use the average displayed by a computer, you might get this readout, right? If you type some stuff into your calculator, like if you do 1 divided by 3, you're going to get 6.66, or you're going to get 0.666 repeating forever. And it'll round the last digit up to 7. Here, this number, raw, pulled out of a computer, would give you this number of digits. But because some of the measuring units that were used to compile all of this data were not as good as the others, we have to use 0.7, because that's as certain as we can be. So the uncertainty is indicated by the last reported digit. So scientific numbers are reported, right? So every digit is certain except the last one, which we estimate. Here, the first 4 digits are certain, and the last one's estimated. The greater the precision of the measurement, the greater the number of digits reported. So here we would have 5 significant figures. Because even though this is estimated, it's still significant, because it tells us where that estimation is. We'll get to that, though. So we're going to take this quarter and measure it on this ruler. Fortunately, they have lines, and I can zoom. Right, so we have, this is 20, this is 25. So this right here must be 24, but where exactly it lies in between 24 and 25 is uncertain. So this is where we make our best guess. And when you do stuff in the lab, this becomes really important because you'll have to measure stuff like this. I'm trying to remember if next week we're doing that lab. I think we are. So you have to measure stuff, and you have to guess at this last digit. So a reasonable guess here, I mean, it looks like to me, so good you guys can see it. Yeah, I mean, it looks like it's a little bit past halfway. So you can call this 24.6. Maybe you think it's a little bit farther than that, 24.7. But that's why there's uncertainty in that last digit, because you can't say for certain where it is. Definition of uncertainty, and they came up with 24.6. You wouldn't say, actually let me go back to this, but you wouldn't say that this is, you might. I wouldn't say that this is 24.5. Just from eyeballing it, you can see it looks a little farther to me. Anyways, we got more examples of this. So this balance has markings every gram, so we estimate to the tenths place. So you always estimate one place farther than the most precise units. So we got 1 gram. So to estimate between markings, right, mentally divide the space into 10 equal spaces and estimate the last digit. So again, we'll zoom in here. Yeah, so this is here, this one's 1 gram. And it's just a little bit farther than that, but it's also kind of a low-res image. It's a little bit blurry. Probably call this 1.2. You might call it 1.3. Looks a little too far to me for 1.1, maybe. I swear I'm not looking beforehand. 1.2 is what we have, or is what the slide says. So you're always estimating a little bit farther. Again, now we have a scale markings to every 0.1 gram. We estimate to the hundredths place, right? One place past a tenth is a hundredth, a thousandth, 10,000th. So the correct reading it says here is 1.26. I'll be the judge of that. So we got 1. So this would be, use a different color. Right, so we have 1.5 there. It always helps me to identify what are the markings, especially if it's on a digital media like this. You can write on it. It's a hair and it's bothering me. Okay. 1.1, 2. Again, this looks like it's just past that, so I'd say 1.6. I think this was grams. Oh, 1.26. Am I missing something here? Oh, yeah, because this is 1. That's 5. This is 1.2. Yeah, so 1.26. I don't think we actually have an example with the digital scale. If you have a digital scale, super easy. You just write down whatever the digital scale says. The last digit's usually rounded, but it's giving you the number of significant figures. So you never look at a digital scale and say, I don't trust you on those last 2 digits. I'm just going to say it's 11. Not how the digital scale works. All right, so let's say you use a thermometer to measure the temperature of a backyard hot tub. You obtain the reading shown, record the temperature reading to the correct number of digits. So let me zoom this in. Let's see. So this is actually up here. 110. So this is 105. All right, so go ahead and make your own guesses. I wish I had Jeopardy music to play right now. You guys know what Jeopardy is, right? I'm not that old yet. All right. There will be a day. It'll be a sad day. So I would call this one 103.2. Does everybody say 103.2? Nice. It does not matter. I'm not saying 103.2 is the right answer. I'm just saying that's what I got. Yeah, no, but that's the uncertainty. So, and this is where it becomes important in your labs that you write everything that you do down, because when I do those when I grade your labs, I'm going to have like an Excel spreadsheet. I'm going to type in your numbers and check the math that way. So for things like this, if you're measuring on a scale that has like a balance or a readout like the ones we saw before, or if you're reading a temperature reading, yeah, I mean, you're just guessing at that last digit. So as long as it's in the ballpark, like you wouldn't call this 103.9. Is there a radio station around here? I think it is. So, but yeah, so this would be like 103.2, 0.3, 0.1, something like that, in that range.